Advection aufgelaufen ist. Elektrik eigentlich. Nein, das ist beim Szenario, oder? Ja, der verloren werden.
Okay, shall we continue? So now we have seen the physical and mathematical classification of the linear advection equation and the wave equation. Now we want to look into the discretization of the linear advection equation, so we concentrate on that. And our first method is the forward time centered space scheme that we also use for the heat equation. So we try it now also for the linear advection equation. So that's the forward time centered space. FTCS scheme. Now applied to the 1D linear advection equation. Equation 1 that we saw at the beginning. Now, how does that look like? Well, we take the usual time derivative that was then the forward time. We essentially use the explicit Euler method there to get from time level n to time level n plus 1. So this is the discretization of the time derivative. And on the right hand side, or in that case it will be our advection term, C, and also on the left hand side. If we take there the central discretization, for the first derivative, we would do it as uj plus 1, that would be at the old time level, minus uj minus 1 at the old time level, divided by 2 delta x. That would be 0. So that would be the forward time centered space scheme for the linear advection equation. We can characterize that again by our stencil or difference molecule, and in that case it would look like we have xj minus 1, xj, and xj plus 1. So, and then we have the new time level here. So that would correspond to time level n plus 1, time level n, grid index j, j plus 1, and j minus 1. So this is space, this is time. Because now j minus 1, j plus 1, and j are involved at the old time level, n, so they are represented here. And the one that we want to calculate is then here. So this is essentially done without thinking too much, and we will see that will it turns out will not be such a good idea. But first we try to analyze it. We can find out by doing Taylor expansions that the truncation error is of order delta t, because it's explicit Euler in time, first order in time, because we are central in space, second order in space. So that is a good thing that it's second order in space. Now, to do the analysis regarding stability, we write it in a little bit different form, also in the form that we would also program it. So the forward time-centered space scheme can be written as, that is the following form. We have ujn plus 1 is equal to ujn. Then we multiply by delta t, and we bring this on the right hand side. And we already did this one. And on the right hand side, we'll get then c times delta t divided by delta x. And that will actually write 2 delta x. And then we have here the uj plus 1n minus the uj minus 1n. There is a certain number appearing that will play an important role further on, and it is this number here. And that has a special name, and that is quite important. So that is the number. We call it here in the lecture C. In the book it is called mu. I don't like it because mu is kinematic viscosity. So therefore we call it big capital C. That is defined as the advection velocity c times the time step delta t divided by the grid spacing delta x. So physically it's the ratio of the distance traveled by our advected quantity u in the time delta t with respect to the grid spacing. And that is called Courant number. Sometimes also CFL number after Courant Friedrichs-Levy. We will hear that in a minute also. And that is due to Richard Courant, of German origin, but later on he founded the Courant Institute at New York University. And what we want to do now is to do a von Neumann stability analysis to see what are the stability properties of this scheme. That will be similar to what we did for the forward time-centered space and also the implicit Euler method for the heat equation, but now we apply it to this discretization of the linear advection equation. So this technique that we learned is quite general. So we do that for the forward time-centered space scheme that we have now written in the form 14. What we do is we insert Fourier mode, in which the discrete solution can be decomposed. That is the amplitude of a wave with a wave number k at the time level n times a trigonometric expression which we express in exponential e to the I imaginary unit times the wave number k times the grid point xj. We insert this mode for a discrete solution at the grid point xj at the time level tn. It's almost mechanical. And if we do that, we do it in 14, then we have the u hat k n plus 1 e to the I k xj is equal to uk hat n, these are the amplitudes, and e to the I k xj minus, now we can use the current number, this is c half then, this is then now the next one, this is u hat k n times e to the I k xj plus 1. This is minus the corresponding term at xj minus 1. So the amplitude again, wave number k, time level n, e to the I k xj minus 1. And then we divide by e to the I k xj. So we divide by e to the I k xj, the whole equation. And then we get u k hat n plus 1 is equal to, and on the right hand side we factorize the u k n, and then we see here we we have e to the ik xj times e to the ik delta x, because this is xj plus delta x. So then we get here minus c half e to the ik delta x. Here we have just the minus, so we get it with an e to the minus ik delta x. That is then multiplied by the amplitude at the old time level. So that is what we get. And then we see immediately our amplification factor is then the ratio of the amplitude at the new time level divided by the amplitude at the old time level. So it's this what is in the square brackets. That is our amplification factor. So then the amplification factor is then g of k delta x. We have identified that as the ratio of the amplitude at the new time level to the one at the old time level. That is, as we say, this square bracket, 1 minus the current number c half times, and then we have the Euler's formula. Write it just minus ik delta x. So Euler's formula says that this is cosine of the argument plus I sine of the argument. This is cosine, plus and minus doesn't matter. It will be minus I sine. So the cosine will go, but the sine will stay. So by Euler's formula we get that this is 2 times the imaginary unit times the sine of k delta x. So that is with Euler's formula. Then we have the amplification factor in the following form. We give a number 16. Amplification factor can be written as 1 minus. Here the 2 cancels, so we get the current number. Here we have I times sine of k delta x. So we write the imaginary unit first, current number, and the sine of k delta x. So that is our amplification factor. And now we check the stability condition. Stability condition is that the absolute value of this must be smaller or equal than 1. And we now use the beta, call this now beta, that has to be smaller or equal than 1. As we argued when we introduced that, it is equivalent to saying that the absolute value squared is smaller or equal than 1. Why do we do that? Because then we can easily compute this modulus of amplification factor squared, because that is simply the real part squared plus the imaginary part squared. So that is then equivalent to the real part of g of beta squared plus the imaginary part of g of beta. Is the beta, and let's see here, squared. Let's see if we can get right here. We have 3 brackets in the end. Yeah. So what is the real part in our case? That is, should be 1. The real part is 1. So that is easy. 1. Imaginary part is I c sine, so it is minus c sine of k over its beta. We're talking here about, so it's beta now. So that is the imaginary part, that is squared. So this gives then c squared sine squared. That has to be smaller equal than 1. 1 plus c squared sine squared of beta has to be smaller equal than 1. That has to be true for all beta. That is clearly not the case. So that means g of beta squared small equal 1 for all beta that are interesting for us. They are small equal pi. So pi, we argued, that is the wave that is the largest wave number for the pi mode. Just a remark on that. We have x here, we have our domain, then we have our u here, we could represent, say, a solution, we have a plus, minus, we could represent a solution that is oscillating from one point to the other. You see that the wavelength of that is 2 delta x. So then the wave number is 2 pi divided by 2 delta x, which is pi over delta x. So that means that the k max is pi. The beta max is then pi. That is the largest wave number that we can represent on the grid. So therefore we can limit ourselves. But it's trigonometric, so we will cover everything when we have this argument. But clearly this is not satisfied, because we can just choose beta not equal 0 or pi, and c not 0, then this will always be greater than 1, because we have 1 plus something. So that means that in our case here, the g of beta squared is greater than 1 for beta not equal 0 plus minus pi, and c not equal to 0. So that means this condition is not satisfied. So from that, we can conclude that the forward time centered space scheme that we considered, that was I think number 13, for the linear advection equation is unstable. That means useless. You will see that when we do the exercise 6. You can try it, but it explodes almost immediately. You can just throw it away. We cannot use it. So it was not a good idea to do this. We did it without thinking, because for the diffusion equation or the heat equation, it was a good idea. Why? Because if we have there something, say we have discontinuity or whatever, but they will have a propagation in both directions. There is no direction is preferred for the heat equation or the diffusion equation. So the central discretization, treating things equal in all directions, is a good idea. We saw it works, it is stable. We have also stability condition there, but we can get it stable easily. But in this case, we have a hyperbolic problem. And then by using the stencil that we have been using, this is time, this is space, where we have a point here, here, and here. We want to go here, and if we have characteristics that go in this direction, this point here will have no influence at all what is happening here. So So this was not a good idea. What we shall do now is we shall take the propagation direction into account. That is, when we do the discretization of the space derivative, we look where the flow is coming from, in that case from the left. So we have to do a difference approximation taking the values in the direction where the flow is coming from into account. Then we shall see it will work. So then we take physics into account and we do that. And that is then the upwind method. So that gives us then a scheme that we can use. That is the explicit upwind method. Which is also called the upstream differencing method. So there we do what we just argued. We have the stencil, then if we are here, and then let's see, we just take the points into account that we are interested in. So this is then the J1, and here we have the J minus 1, and here we have time level n, and here we have the time level n plus 1. This is the situation that is important. That is the situation for C positive, propagation from left to right. So we look in the direction from which the wind is blowing. That is, in that case, the upstream direction is then to the left. So then we move this into account. Downstream has no influence on what is happening here, not at all. It influences something to the right, but nothing here. So that is then the right way to do it. And when you do the this scheme for C negative, it will just be the opposite. If C is negative, then we take the J plus 1 into account, and the J, but not this one, because then everything is going from right to left. This scheme. So we take the difference approximation. Of the u dx in the upwind direction, upstream direction. Then to the following. We have the time derivative. We stay still with the explicit Euler method. Ujn plus 1 minus the Ujn divided by delta t plus c. But now we take the backward difference. Ujn minus Uj minus 1n. Now it's just divided by delta x. That is equal to 0. And if we think of it carefully, for our grid points 0 to nj, we see we cannot do it for j equals 0. And we must not do it, because there we will have the boundary condition. We must give a boundary condition at the left boundary. That is for j equals 0 in that case. But we can use this from j, from 1 on up to the last one that we call nj. That will be at the right boundary. There we can compute it, just ordinary computation So that is as it should be. So that is our Upwind method. That can also be written in another form that will be useful, say, for the programming and also for the stability analysis. The ujn plus 1, so we multiply again by delta t and bring everything on the old time level to the right hand side. Then we have here the ujn minus, we get then the advection velocity c times delta t divided by delta x, that is the current number c, times ujn minus uj minus 1. That is then to be taken at the similar j's as we have here. So again, to remind you, the c is the current number. C, level c times delta t divided by delta x. The current number. So, you can easily do the consistency analysis to find the application error. It turns out that is of order delta t and delta x. So that you can do it as an exercise. So that means this method is first order in space and first order in time. That we can see from that. So what else can we say? When we have x, we look now in the xt diagram. We have now t here. We have our midpoint xj here. And if we have, say, our midpoint xj minus 1 here, then this will be our grid spacing delta x. So that will be in delta x. And in this direction, we want to compute the solution at the new time level. So that here would be then, say, n delta t, the time level. This would correspond to the time level n plus 1 delta t that we want to compute. Now, what we want is that we want to compute the solution essentially, as we say here, by means of uj at the old time level, which is also appearing here, and uj minus 1n, by these values here. So, and what we see here is a kind of interpolation between these. An interpolation between uj, which has a 1 minus c, and this has a c in front. So it's a kind of interpolation. So that is what numerics is. So for numerics, we want to use the values here and here to determine the solution. What does the exact solution say? The exact solution says, just take the characteristic through this point. We want to know the solution here. So we look at the characteristics through this point here, and then we might get down somewhere here, where we have where we come from, where the solution is coming from. So that would be then a way to get the exact solution. We would have this situation here. Then we would have, that would be then on a characteristic. This would be then on a characteristic. The x of t dt is equal to c. So this would be then, and here again we have the situation that c, I stress that again, is positive. So then the solution would be determined by this point here. This point here. What is this point? We know it. Because this is delta t, and this distance that is traveled within the time delta t is c times delta t. So this distance here is c times delta t. So that means it is xj minus c delta t. That is the point. So therefore we can argue, in order that our scheme should make sense, using these points for computing the solution, the exact solution, that is the origin of the characteristic going through the value that we want to compute, should be within this interval. So that is to say that the exact domain of dependence regarding this point is the point here. That point should be within the interval xj minus 1 and xj. So that is what we require, such that our scheme makes sense. If that would not be the case, then we couldn't say very much. As in the case that we had for the central scheme, this point here doesn't have any meaning. If this characteristic would come down here, then things would be determined what is happening here at the neighbor point, but this would not have any influence. So we want this point where the characteristic is coming from, the characteristic through the value at the new time level at the point that we want to determine. This point here, at the old time, that is within the interval of the points that we use to determine the numerical solution. So we can argue that, or say that in the following way. The exact domain of dependence and we always talk now about the value that we want to determine, xj and tn plus 1. The exact domain of dependence, that is the point xj minus c delta t. So that is the one that determines the solution where we want to have it. That is then for the domain of dependence, just the point in this case. That point must be contained in the numerical domain of dependence. And that is the interval xj minus 1 to xj. Because there we use the solutions that we have there, ujn and uj minus 1 to determine the numerical solution. So, exact domain of dependence, numerical domain of dependence. And that means that the point 20, that the point xj minus 1 should be smaller equal than xj minus c delta t. That should be smaller equal than xj. Then this point where the characteristic comes from the old time level, will be then in this interval. Then it makes sense to use these 2 points for determining the solution. And this is xj minus delta x. This here is xj minus delta x. So then we can see that this condition is satisfied if c, the advection speed, is positive, or the current number is positive, or 0, then it's also okay. And this situation here is satisfied if delta x is greater equal than c delta t. That means that the current number is smaller equal than 1. So then we get from that the stability condition. So that means this condition 20 is satisfied for, that is 21, 0, smaller equals c, and that is now the current number, 1. And c again is, I write again, c delta t divided by delta x, the current number. So that is the condition that we get from this argument. And this condition is called the CFL condition. And that goes back to the people who first came up with it. That was the Richard Courant, Felix, and Levy. And that is actually dating back from 1928. And they used it for showing well-posedness for initial value problem using the finite difference method. And there they found out that we need this condition. So, what can we see with that? We can see that if this condition is satisfied, that in the scheme that we derived, that was our scheme, let's see, I think 17, let's see, 17 was the original one, then in 18, so 18 can be written as 18 can be written as ujn plus 1 is equal to, and that is 1 minus c times ujn plus c times uj minus 1n. If you look back to that, you can see that. Ujn minus c uj, that is this one. Then we have minus c minus plus c ujn. So that means when we have this condition, these coefficients are positive. So this is what Rader has also been using for the derivation of the stability condition. So then this is satisfied. And this is actually then, as you see, an interpolation of the value at this point. Because what the C is the as we said here, C is C delta T over delta X. C delta T is this divided by delta X. So if say if we have this equal to 1, then it means that the characteristic will come from this point here. So that is a special case, but in that case, then this would be 0 and this would be 1. In the case when we had the slope 0, c would be 0, the advection speed, no movement at all, then the characteristic would come from here. So then the solution would be the value from xj at the old time level, and that would be the situation when then the c is 0, also the capital C, then we would have this situation. So what we have here, you can find that out if you do it, is simply a linear interpolation of the solution at this point here, at xj minus c delta t, using the values that we had at the old time level at xj minus 1 and at xj. So then we get this result. Okay. So let's see, already with the time. Managed to see the example. Okay, but I think we are on overtime anyway, so I can show that tomorrow, an example where we can use this method. That will be also the method that you are going to use and to analyze for exercise 6. Okay, so you have an idea now of the Upwind method for advection.